Finally, let's talk briefly about soundings. I know these diagrams can be pretty intimidating if you're just seeing them for the first time or just getting into severe weather forecasting and storm chasing, but they are one of our most critical tools that we can use when making a forecast, so it's definitely worth inclusion. We're just going to give you some basic tips about how you can tell whether or not a sounding is favorable for severe weather. So basically these soundings come from the weather balloons that are released by the National Weather Service offices every morning and evening. They usually release them at 7 a.m. Central Daylight Time and 7 p.m. Central Daylight Time, sometimes during the middle of the day as well, sometimes around 1 p.m. Central Daylight Time. Just depends on the day. If there's more active weather, they will release more balloons. If it's a quieter day, they might just release one balloon in the morning, one in the evening. So the weather balloons are equipped with instrument packages that radio back data that consists of temperature, dew point, pressure, winds, etc., all the way up into the atmosphere until it pops, basically. What the Weather Service gets back is a bunch of raw data that's manipulated into a nice looking diagram that looks like this. This is an example of a nice sounding that's been compiled by sounding software. After the raw data has come back, this is what it looks like. So the sounding is basically split into two main parts. On the left here, we have the Skew-T, and on the right, we have the Hodograph. We'll start here on the left with our Skew-T diagram. This is showing us the thermodynamics in the atmosphere at that given location that the sounding was released from. This is basically involving our temperature and how moist, how dry, how unstable our air is. So we're not going to go through all the intricate little lines on the diagram, but let's just show you what the main features are. So on the x-axis here, the bottom axis, this is temperature, so I'll put T down there, and this going up on the y-axis here, the vertical axis, that is height, given in pressure, so 1,000 millibars, 850 millibars, 700 millibars, and so on and so forth. So this red profile here is the atmospheric temperature. So it's the temperature that the balloon senses as it goes up in the atmosphere. The green profile is the dew point profile. So that is basically moisture that the balloon measures as it goes up in the atmosphere. These two can tell us a lot about how moist and how dry the air is. When these two lines, when the red temperature profile and the green dew point profile are far apart from one another, like you see at this level here, that indicates dry air. When they're closer together, as you see in the lowest couple kilometers here of the sounding, that indicates a much more moist environment. So when those lines are closer together, more moist. When they're farther apart, it's a drier atmosphere. Generally, we want to see fairly deep moisture in the low levels, that temperature profile and the dew point profile fairly close to one another through a decent layer of the atmosphere. Now, there's not any set threshold here, but at least, a kilometer or two off the surface, this is a nice deep moist layer of moisture here in the low levels of the atmosphere. That usually tends to be below a bit of drier air aloft. Now, too much dry air can be a bad thing, but when you have that drier air atop a little bit more moist air, that can create instability. Now, the other piece of this is this brown dashed line here. That is the parcel trace. So think about the air at the surface. Think about taking just one sort of hypothetical box of air. Let's take a cardboard box, get rid of the sides of the box, but we have a box of air that's a box that's just full of air at the surface. The parcel trace is basically the temperature that the parcel would take on if it were to be released into the atmosphere and be able to rise on its own. We want the parcel then to be warmer than the actual environment. So when this parcel trace, this brown dashed line here, is to the right of the environmental temperature profile, the red profile here, the atmosphere is unstable. So for all of this distance here into the atmosphere, we have instability because the parcel trace is to the right of the temperature trace. That means at all this level where I've shaded in pink, that parcel would be able to rise on its own. Therefore, that part of the atmosphere is unstable. When the parcel trace is to the left of the temperature profile, like you see right in there, that is some semblance of capping. That means that the parcel is colder than its surrounding environment and therefore will not be able to rise on its own. For severe weather, we want there to be instability throughout the entire atmosphere. We want there to be the situation where a parcel can really rise on its own throughout the entire atmosphere. Now, it is somewhat good to have a little bit of this cap in place early on in the day, going through the morning into the afternoon of a severe weather event, because that can actually hold storms off from firing and allow more and more instability to build. Once that cap is broken later in the afternoon through things like sunshine, warm air, moisture transport, cold air transport aloft, things like we talked about earlier in episode 1 of this series, that can actually allow the cap to break or erode, and then the environment at that point is fully unstable. So again, just to summarize here, we want the environment, we want that parcel trace to be to the right of the temperature profile throughout the entire atmosphere. And we don't want to see any of these once storms are able to initiate. We don't want to see any of that capping left, but capping can be good early on in the event through the morning and into the part of the afternoon to help build more and more instability in the environment.
Getting home alive is the goal. That's why these rules matter. Free ebook link in description.
Let's move over to our Hodograph now. This is basically just a plot of all the winds in the atmosphere. So it's a little bit difficult to simplify this down, but basically think of this, instead of being a regular graph that has X and Y coordinates like our Skew-T, it has X coordinates of temperature on the horizontal axis and Y coordinates of height in pressure on the vertical axis. Well, that's not what this Hodograph is. This is basically a circular graph that is basically made up of magnitude, these circles here, and angles. So we basically draw the winds, draw the wind vectors as kind of arrows. So basically that lowest point of the Hodograph is our surface. Our surface winds are out of the southeast at 10 knots. You see that wind barb there. So basically this surface point is showing us where our winds are there at the surface. So if we were to draw an arrow there, that point at the end of that arrow would be what is plotted on the Hodograph, and then we just connect the dots all the way up through the atmosphere. Now, just keeping this simple, the shapes that you want to see for the Hodograph for severe weather, you want to see more elongated Hodographs, more lengthy Hodographs. If you see all of these points kind of on top of one another, and you have just kind of a mess of lines that really is very small in its extent, that means that your deep layer wind shear is on the weaker side, which is not favorable for severe storms. When you have longer Hodographs like this, that means that you have stronger deep layer shear, which is able to allow the storms, as we talked about in episode 1, to become tilted and rotate and organize themselves into severe storms. For tornadoes, we want to see more of a meat hook type shape. So we want to see some curvature in the lowest levels of the Hodograph, which is this red portion here. That's the nice thing about this sounding source I'm using from the Storm Prediction Center. They color code these different segments of the atmosphere. So red is the lowest 3 kilometers, the light green is from 3 to 6 kilometers, and so on and so forth. So we want the portion in the lowest kilometer or so of the atmosphere to have some nice curvature to it in the clockwise direction. As you see here, this is a good example of that. Nice clockwise curvature in the Hodograph. That means we have strong low-level shear, which is favorable for tornadoes. Again, there are some special cases where we don't see strong low-level shear for tornadoes, but for the most part, this kind of meat hook type shape is more favorable for tornadic activity than a straighter Hodograph. If we have just a straight line Hodograph, that favors more large hail and damaging winds, not so much of a tornado risk. So those are just some basic tips to help you at least identify if a sounding is favorable or not favorable for severe weather. Again, we want to see an unstable environment where our parcel, the brown dashed line here, is to the right of the red profile. We want to see fairly deep moisture so that the temperature and the dew point profiles in the atmosphere pretty close to one another up through the lowest couple kilometers there of the atmosphere, and underneath some somewhat drier air aloft to help build that instability. And then for our Hodograph, we want to see longer Hodographs, a longer profile overall. For tornadoes, we want to see that Hodograph have a lot of curvature in the clockwise direction in the lowest levels of that Hodograph. And for large hail and damaging winds, typically we see that with more straight line Hodographs.
Remember to check out those links in the description below, and then watch another video.